This is a recast of the 7,800-word piece, Capsule Networks, CapsNets, from Schnurpat.com. This article discusses the concept of capsule networks, CapsNets, in machine learning, highlighting their advantages over traditional neural networks, such as convolutional neural networks, CNNs. CapsNets aim to overcome the limitations of CNNs by capturing hierarchical relationships between object parts and encoding spatial information. They have shown promising results in image recognition tasks, offering better performance in handling variations in pose, viewpoint, and occlusions. However, CapsNets are still in the early stages of development and face challenges such as training difficulties and computational complexity. Despite these challenges, CapsNets have the potential to revolutionize various domains, including computer vision and natural language processing. Let's listen in.
Today, we'll be talking about a recent advancement in the field of machine learning called capsule networks, or CapsNets for short. These networks aim to overcome the limitations of traditional deep learning approaches, such as convolutional neural networks, CNNs, which have revolutionized the field of machine learning in recent years.
That's right. CNNs have allowed computers to perform complex tasks like image recognition and natural language processing with remarkable accuracy. However, they do have their limitations. One of the main issues is their inability to learn hierarchical relationships between object parts. This means that CNNs struggle with understanding the spatial relationships between different features in an image.
And that's where CapsNets come in. Developed by Geoffrey Hinton, the creator of deep learning, CapsNets aim to address these shortcomings by introducing the concept of capsules. Capsules can be thought of as groups of neurons that not only capture the presence of an object in an image, but also encode important properties of the object, such as its position, orientation, and scale.
Exactly. By incorporating capsules, CapsNets enable dynamic routing between them. This means that the output from one capsule is used to weigh the predictions of other capsules in the layer above. This routing creates a more holistic understanding of the image and allows for better generalization, improved object recognition, and robustness to variations in scale and viewpoint.
It's important to note that CapsNets represent features using vectors instead of scalar values like traditional neural networks. This vector representation allows CapsNets to encode spatial information and pose relationships between object parts. This is a more intuitive and robust way of representing structures in an image.
Absolutely. And this novel approach has shown promising results in various image recognition tasks. For example, CapsNets have demonstrated better performance in recognizing objects with different poses and handling occlusions compared to CNNs. This signifies the potential of CapsNets in advancing the capabilities of deep learning algorithms.
Right. CapsNets have the potential to revolutionize the field of image recognition and inspire further advancements in machine learning. By capturing hierarchical relationships between object parts, CapsNets provide a more holistic understanding of complex objects in images, leading to improved accuracy and robustness.
However, it's important to mention that CapsNets are still in the early stages of development and face challenges such as training difficulties and computational complexity. But with further research and advancements, CapsNets could pave the way for new possibilities in various domains, including computer vision and natural language processing.
That's true. Machine learning in general has significant significance in various industries. It allows computers to learn from data and make predictions or decisions without being explicitly programmed. This ability to recognize patterns and make accurate predictions has applications in fields like healthcare, finance, marketing, and transportation.
Absolutely. ML algorithms learn from historical data by identifying underlying patterns and relationships. They then use this knowledge to make predictions or decisions on new, unseen data. This can lead to better outcomes, improved decision-making, and automation of processes.
And as technology continues to advance, the significance of machine learning is only expected to grow. It has the potential to revolutionize how we solve complex problems and make informed decisions.
So in summary, capsule networks or CapsNets are a promising approach in the field of machine learning. They aim to overcome the limitations of traditional neural networks by capturing hierarchical relationships between features. By encoding spatial information and pose relationships between object parts, CapsNets provide a more intuitive and robust representation of complex objects in images.
That's right, Ben. Traditional neural networks, also known as feed-forward neural networks, have been widely used for machine learning tasks. They consist of multiple layers of artificial neurons, where information flows from the input layer to the output layer without forming any loops or cycles. These networks have limitations, such as difficulties in recognizing variations in orientation, scale, and pose.
Absolutely. That's where convolutional neural networks, or CNNs, come into play. CNNs have gained significant popularity in image recognition tasks because they exploit the spatial structure of images through convolutional layers and pooling layers. Convolutional layers learn local patterns by sliding filters across the input data, while pooling layers downsample the extracted features and provide translation invariance.
However, CNNs still have their limitations. One major limitation is their inability to effectively handle spatial hierarchies. While CNNs can identify features in image, they struggle to understand the spatial relationships between these features. This makes them less accurate when it comes to distinguishing objects under certain transformations or occlusions.
And that's where capsule networks, or CapsNets, come in. CapsNets aim to overcome the limitations of CNNs by introducing capsules, which are groups of neurons that encapsulate probability distributions of visual features. These capsules work together to form a rich and dynamic representation of an object, allowing for better understanding and recognition.
Right. CapsNets use a new type of layer called the routing by agreement algorithm, which allows capsules in each layer to vote on their predictions and reach a consensus through iterative agreement. This dynamic routing mechanism enables CapsNets to model spatial hierarchies effectively and handle transformations and occlusions more accurately.
Absolutely. With its ability to handle interclass variability and geometric transformations, CapsNets hold great promise for improving the accuracy and efficiency of machine learning algorithms, particularly in the field of image classification.
That's right. CapsNets have shown great potential in tasks such as image classification, object detection, and pose estimation. The capsules in CapsNets encode spatial information and pose relationships between object parts, making them robust to object rotations, translations, and other geometric transformations. And this is just the beginning. While CapsNets have already shown impressive results in image recognition tasks, there is still a need for further research to explore their potential applications in other domains, such as natural language processing and reinforcement learning.
That's right. CapsNets hold immense potential to enhance various machine learning tasks and pave the way for more advanced and efficient artificial intelligence systems. They could be utilized in object recognition, medical imaging, natural language processing, and robotics, among other areas.
However, it's important to acknowledge the challenges and limitations that CapsNets currently face. For example, the computational cost of CapsNets is significantly higher compared to traditional CNNs, which could hinder their scalability.
Additionally, the lack of large-scale datasets specifically designed for CapsNets poses a challenge in training and evaluating their performance. This highlights the need for further research and exploration to fully understand the theoretical foundations and behavior of CapsNets.
Despite these limitations, researchers are optimistic about the future of CapsNets. As improvements are made to the architecture and these challenges are overcome, CapsNets hold tremendous potential for advancing machine learning and reshaping various industries.
So in conclusion, capsule networks, CapsNets, offer a promising alternative to traditional neural networks by addressing their limitations and providing a more accurate and interpretable approach to deep learning.
Their hierarchical structure, dynamic routing algorithm, and ability to handle orientation and scale variance make them a powerful tool for image analysis and pattern recognition tasks.
With ongoing research and improvements, CapsNets have the potential to revolutionize machine learning algorithms and enhance various applications such as object recognition, medical imaging, natural language processing, and robotics. Additionally, the dynamic routing algorithm introduced in CapsNets facilitates the selection of the most relevant capsules, allowing for better generalization and reducing the reliance on vast amounts of training data. This is a significant advantage over traditional neural networks.
Absolutely. And while CapsNets are still in their early stages of development, they hold promise in revolutionizing the field of machine learning and shaping the future of artificial intelligence. Further research and advancements in CapsNets will undoubtedly lead to even more accurate and efficient models.
Definitely. Now let's dive deeper into the main points of the article. First, let's understand what capsules are and how they differ from traditional neural networks.
That's right. Capsules are groups of neurons that work together to encode the properties of a specific entity or part of an image. They can be seen as small neural networks that learn to represent different features of an image, such as shape, orientation, or texture.
Exactly. Each capsule consists of a vector of activation, which represents the probability of the presence of a particular feature, and a pose matrix, which encodes the parameters of the feature, like position, size, and deformation. This explicit representation of features allows CapsNets to better handle variations in pose, scale, and viewpoint.
And that's where dynamic routing comes into play. Capsule networks incorporate the concept of dynamic routing, which enables better interpretation of complex relationships between different capsules. This routing mechanism determines the weights of connections between capsules in different layers based on the agreement between the predictions of higher-level capsules and the actual outputs of lower-level capsules.
Right. This iterative process significantly enhances the robustness and stability of capsule networks by actively engaging the capsule's ability to learn from each other. As a result, capsule networks excel in capturing hierarchical relationships and accurately representing spatial reasoning.
Absolutely. Capsule networks are particularly promising for tasks involving image recognition and object detection because they can capture spatial relationships and handle variations in viewpoint more effectively than traditional neural networks.
Definitely. Now let's discuss the dynamic routing algorithm in more detail and its role in CapsNets.
The dynamic routing algorithm is responsible for routing information between capsules and ensuring that the output of each capsule is correctly routed to the relevant higher-level capsule. It helps capsules learn relationships and hierarchical structures in input data, enhancing the network's ability to understand complex visual patterns.
Right. This algorithm iteratively updates the coupling coefficients, which represent the probability of two capsules being related. By routing information in this way, CapsNets can capture spatial relationships of features and preserve viewpoint invariance.
Absolutely. The dynamic routing algorithm has shown significant improvements in the performance of CapsNets in various tasks, including image classification and object detection. However, researchers are continuously working on developing more efficient routing algorithms to further enhance the capabilities of CapsNets.
That's right. Now let's compare CapsNets with traditional convolutional neural networks, CNNs, to understand the advantages of CapsNets.
Convolutional neural networks excel at extracting hierarchical features using convolutional layers, but they have limitations in their translation invariance properties and handling variations.
On the other hand, CapsNets overcome these limitations by utilizing capsules, which encode the instantiation parameters of a specific entity. Capsules create vectors that represent the probability of the entity's presence and other properties, such as size, orientation, and deformation.
And by using dynamic routing, CapsNets efficiently process spatial hierarchies and handle changes in the relative spatial relationships between objects. They can generalize to variations in the viewpoint of an object, unlike CNNs.
However, it's important to note that CapsNets still face challenges in training large-scale networks and lack interpretability due to the complexity of their routing algorithm. But comparing CapsNets to CNNs highlights the unique contributions and potential improvements that CapsNets offer in the field of image recognition and computer vision.
Absolutely. CapsNets represent a promising advancement in the field of machine learning. They introduce capsules as a new unit of neural network that can encode multiple properties of visual concepts and improve robustness and efficiency. The dynamic routing mechanism enhances spatial relationships and generalization.
And while CapsNets are still in the early stages of development, their potential for revolutionizing image recognition and understanding tasks is indisputable. Further research and experimentation will likely refine and enhance this innovative approach.
That's right. One of the major advantages of CapsNets over traditional convolutional neural networks, CNNs, is their ability to handle changes in viewpoint or perspective. CNNs often struggle with recognizing objects or patterns when they are viewed from different angles or orientations. But CapsNets use vector outputs called capsules to represent different properties of an object, such as its position, scale, and orientation. These capsules are then combined to form a higher-level representation of the object.
This means that CapsNets are inherently more equipped to handle variations in viewpoint, making them more robust and reliable in real-world scenarios. They also offer better interpretability as the vector outputs of capsules provide insights into various aspects of an object's existence. CapsNets also promote hierarchical reasoning, allowing the network to understand the relationships between different objects and their parts.
So CapsNets have the potential to revolutionize computer vision tasks and contribute to the development of more intelligent and adaptable systems. Another advantage of capsule networks is their ability to handle part-whole relationships effectively. Traditional CNNs struggle with recognizing objects in complex scenes due to their inability to capture hierarchical relationships. But capsule networks have a natural capability to encode part-whole relationships in their architecture.
Each capsule in a CapsNet represents a specific part of an object, while the activation of the capsule determines the instantiation parameters such as pose and deformation. By considering the spatial relationship between different parts, CapsNet can effectively capture the hierarchical structure of objects, making it more robust to variations in viewpoint and occlusions.
This feature enables CapsNet to better understand natural objects and their various configurations, which is crucial in tasks such as object recognition and image synthesis. Hence, the ability of capsule networks to handle part-whole relationships gives them an edge over traditional CNNs when it comes to dealing with complex and ambiguous visual scenes.
Another advantage of capsule networks is their robustness against various transformations. Traditional CNNs are highly sensitive to changes in an input image, such as rotation, translation, or scaling. However, capsules address this limitation by encapsulating information about different visual features and their spatial relationships.
Capsules can learn to encode specific properties of a feature, such as its orientation, color, or shape, and preserve this information across different viewpoints or transformations. This capability allows capsule networks to accurately identify objects even when they are presented in unfamiliar perspectives or orientations. The transformation invariance of capsules is achieved through dynamic routing, which allows the capsules to reach consensus on the features present in an image.
The ability of capsule networks to handle various transformations makes them suitable for real-world applications where images might undergo unpredictable changes. For instance, in autonomous driving, robustness against transformations is crucial for accurately detecting objects from different angles or under varying lighting conditions. Overall, the robustness of capsule networks greatly enhances their practical usability in scenarios where traditional CNNs may struggle.
And let's not forget about interpretability and explainability. Capsule networks offer a novel approach to address the challenge of interpretability in machine learning. Traditional neural networks lack transparency, making it difficult to understand how exactly they arrive at their decisions. But CapsNets aim to provide more meaningful explanations by utilizing capsules.
These capsules encapsulate various properties of an object, such as its pose, presence, and deformation. By preserving hierarchical relationships and spatial arrangement, CapsNets enable a more accurate representation of objects in the data, enhancing interpretability.
This architecture allows for a more granular understanding of the decision-making process, as capsules can activate or deactivate based on their agreement with higher-level capsules. Furthermore, the dynamic routing mechanism within CapsNets enables the assignment of weights to the input capsules, reflecting their importance in the overall prediction.
With this enhanced interpretability and explainability, CapsNets show promise in domains where transparency is crucial, such as healthcare and finance, as they allow experts to comprehensively understand and trust the decision-making process of the model.
In addition to their ability to model spatial hierarchies, CapsNets also possess other advantageous features. One crucial attribute is their capacity to learn relationships between entities. Traditional CNNs operate by pooling and traversing feature maps to detect patterns. However, CapsNets are equipped with capsules, each representing an instantiation parameter of an object.
These capsules encode information about the object's presence and pose in the input data. By measuring the agreement or disagreement between capsules, CapsNets can infer the relationships between different objects in an image. This enables these networks to handle complex configurations, occlusions, and deformed objects, which are challenging for traditional CNNs.
Moreover, CapsNets have proven to be more robust against adversarial attacks, where slight perturbations are introduced into the input data to confuse the network. They achieve this resilience by making it computationally expensive to perturb their outputs. Overall, CapsNets present a promising alternative to CNNs, offering distinct advantages in terms of modeling spatial relationships and resistance against adversarial attacks.
Absolutely. And one area where CapsNets have shown great potential is in computer vision tasks, such as image classification and object recognition. Traditional CNNs have been widely used for these tasks, but CapsNets offer superior performance.
That's right. CapsNets are able to capture rich spatial relationships among different components of an object, allowing for more accurate object recognition. They can handle viewpoint changes and occlusions, making them more robust and efficient in classifying complex images.
And let's not forget about the dynamic routing algorithm used in CapsNets. This algorithm allows capsules to interact with each other and refine their predictions based on agreement between predicted and actual outputs. This iterative process enhances the performance of CapsNets and improves their ability to recognize objects.
Absolutely. The dynamic routing algorithm allows CapsNets to capture hierarchical relationships in text by encoding the dependencies between words and phrases. This results in more accurate and interpretable predictions in tasks, such as text classification and sentiment analysis.
And this has significant implications for natural language processing, NLP. NLP involves the processing and analysis of large amounts of text data, allowing machines to extract meaning, sentiment, and context from human language.
Right. NLP has transformed various industries, from healthcare to customer service, enabling chatbots and virtual assistants to better understand and respond to human queries. CapsNets have proven effective in NLP tasks, such as sentiment analysis and machine translation, offering more accurate and efficient language processing.
Another exciting application of CapsNets is in the field of healthcare. Medical imaging is crucial for diagnosis and treatment planning, and CapsNets have shown promise in enhancing this process. They can identify lung nodules, detect tumors, and classify retinal diseases with impressive accuracy.
And this is because CapsNets can capture richer spatial relationships within medical images, allowing for more precise analysis. This is particularly important when it comes to discerning subtle differences and relationships between tissue structures.
Absolutely. CapsNets have the potential to greatly improve accuracy and efficiency in healthcare applications, leading to more effective patient outcomes and overall improvements in healthcare practices.
However, it's important to note that CapsNets are still a relatively new concept in the field of machine learning. There are still some challenges that need to be addressed.
One challenge is the training of CapsNets on large-scale datasets. The dynamic routing algorithm can be computationally expensive, so efforts should be made to optimize this process and make it feasible for real-world applications.
Another challenge is the limitations of CapsNets in handling complex transformation, invariances, and occlusion. Further investigation is needed to address these limitations.
Despite these challenges, CapsNets hold great potential for various applications, including image recognition, voice recognition, and natural language processing.
Absolutely. Capsule networks have the potential to revolutionize various fields due to their unique abilities. They offer superior performance in computer vision tasks, such as object recognition and image classification, compared to traditional CNNs. They are also effective in natural language processing tasks and have shown promise in healthcare applications.
That's right. One of the key challenges mentioned in the article is the computational complexity of CapsNets. The dynamic routing algorithm used in CapsNets requires a high number of iterations, making training and inference time-consuming. Researchers are actively exploring methods to reduce this computational overhead, such as parallel processing and developing more efficient dynamic routing algorithms.
Absolutely. Another challenge is the scalability of CapsNets. As the size of the datasets and tasks increases, CapsNets struggle to handle them effectively. This is because the number of capsules and routing iterations needed also increases. Researchers are working on techniques to improve the scalability of CapsNets, including developing strategies to handle the increased number of capsules and routing iterations.
That's a great point. Another important aspect is the interpretability of CapsNets. While CapsNets are known for their ability to capture hierarchical relationships among features, understanding and interpreting their reasoning behind predictions is still a challenge. Efforts should be directed towards developing techniques to provide explanations for CapsNets predictions and uncovering the underlying mechanisms that enable them to learn abstract concepts.
Absolutely. It's crucial to have interpretability in machine learning models to gain trust and understand the decision-making process. Explaining the predictions of CapsNets would enable researchers and users to better understand how these networks arrive at their conclusions.
Definitely. Now let's move on to the next point in the article, computational complexity and scalability. CapsNets offer potential advantages over traditional CNNs, but come with inherent computational costs. The dynamic routing algorithm adds complexity, leading to increased computational demands. Striking a balance between efficiency and network size is critical for CapsNets to overcome scalability limitations.
Absolutely. Evaluating the resource requirements and scalability of CapsNets is essential for their practical implementation in real-world scenarios. Researchers are exploring various techniques such as parallel computing, hardware acceleration, and algorithmic optimizations to address these computational challenges.
That's right. The next challenge mentioned in the article is the lack of large-scale CapsNet datasets. While traditional deep learning methods have benefited from well-established datasets like ImageNet, CapsNets lack such large-scale datasets specifically designed for them. This limits the ability to accurately evaluate and compare the performance of CapsNets.
Exactly. CapsNets have unique structural characteristics and routing mechanisms that require datasets reflecting these specific characteristics. Obtaining large-scale CapsNet datasets has become essential to unlock the true potential of CapsNets and further research in this field.
Absolutely. Now let's discuss some potential advancements in future research areas for capsule networks. One key area for improvement is the dynamic routing algorithm used in CapsNets. The current iterative algorithm is computationally expensive and limits scalability in large-scale applications. Researchers are actively working on developing more efficient and scalable routing algorithms.
That's right. Another area of exploration is the effectiveness of CapsNets in handling hierarchical structures and spatial relationships. Capsules have shown promise in various domains such as natural language processing, computer vision, and robotics. Further research can explore the combination of CapsNets with other deep learning architectures to enhance performance and capabilities.
Definitely. The potential advancements in future research areas for CapsNets are vast. Continued research in this field holds great promise for advancing the field of machine learning and unlocking the full potential of capsule networks.
Absolutely. Capsule networks have already shown promising results in various domains, but addressing the challenges mentioned in this article and exploring these future directions can make them even more powerful and widely applicable in machine learning applications. One of the main points of this article is the effectiveness of capsule networks, or CapsNets, in different domains. For example, in the healthcare sector, CapsNets have been used for tasks like diagnosing pulmonary nodules in CT scans and detecting diabetic retinopathy from fundus images. In these cases, CapsNets have outperformed traditional convolutional neural networks, CNNs, in terms of performance.
That's right. CapsNets have also been employed in natural language processing, NLP, tasks such as sentiment analysis, document classification, and question answering. The results from these case studies show that CapsNets have the potential to capture complex relationships and hierarchical structures in different types of data.
And it's not just healthcare and NLP. CapsNets have also shown promise in the field of robotics. They have been used for object recognition and manipulation tasks. By incorporating the concept of viewpoint invariance, CapsNets have improved the overall performance of autonomous robots.
These case studies highlight the versatility and applicability of capsule networks in various domains. It shows that CapsNets have the potential to be adopted in real-world applications.
Definitely. The article also provides a detailed analysis of successful applications of CapsNets. In the healthcare sector, CapsNets have improved the accuracy of medical diagnosis by enabling robust feature extraction from medical images. They can capture spatial relationships between different parts of an image, leading to better detection of abnormalities and early disease prediction.
In natural language processing, CapsNets have shown their potential in tasks like sentiment analysis and language translation. Their dynamic routing mechanism allows them to learn and represent hierarchical structures in textual data, resulting in more accurate predictions and understanding of complex language patterns.
And in the field of robotics, CapsNets have been utilized for object recognition and tracking. By considering viewpoint invariance, CapsNets have demonstrated remarkable robustness in recognizing objects from different angles.
Overall, the success of these applications highlights the versatility and effectiveness of capsule networks across various domains.
The article also compares CapsNets with other machine learning models for specific tasks. When it comes to image recognition and classification, CapsNets have shown promising results. They overcome the limitations of traditional CNNs by capturing spatial relationships between features through the use of capsules.
That's right. CapsNets have also demonstrated better performance in tasks such as object detection, pose estimation, and image segmentation compared to CNNs. In natural language processing, recurrent neural networks, RNNs, and transformer models like BERT have been widely used. However, CapsNets have the potential to excel in NLP tasks, as well due to their ability to capture hierarchical relationships between words or concepts.
It's important to note that further research is needed to fully assess the strengths and limitations of CapsNets compared to other machine learning models in various specific tasks.
Absolutely. Continued research in this field will help us better understand the capabilities of capsule networks and how they can be leveraged to enhance machine learning algorithms for image analysis and pattern recognition applications.
And with ongoing improvements and advancements, it's anticipated that CapsNets will play a vital role in the future of machine learning.
That's right. Capsule networks, or CapsNets, have the potential to revolutionize the field of machine learning by addressing the limitations of traditional neural networks and offering a more efficient and accurate alternative.
One of the key advantages of CapsNets is their ability to handle orientation and scale variance, which is a challenge for convolutional neural networks, CNNs. CapsNets achieve this by representing an entity as a vector of attributes, known as capsules, rather than relying solely on feature detectors.
These capsules encapsulate rich information about an entity's presence and capture more nuanced information about objects and their relative positions. This enables CapsNets to better understand three-dimensional objects and handle image deformations.
And with the introduction of transformation matrices, CapsNets are able to be invariant to changes in the pose and orientation of objects. This means that the model can recognize objects accurately regardless of their orientation, leading to more robust and reliable results.
Absolutely. Another advantage of CapsNets is their ability to encode spatial as well as part-whole relationships. This hierarchical structure allows CapsNets to capture complex patterns and understand the relationships between different parts of an object.
This is in contrast to traditional neural networks that rely on max pooling mechanisms and struggle with handling occlusions. CapsNets can overcome these limitations by efficiently analyzing high-dimensional data and capturing intricate patterns through dynamic routing.
Dynamic routing plays a crucial role in ensuring effective communication between capsules and the creation of hierarchical relationships. This allows CapsNets to capture more detailed information about objects and improve feature identification.